Hello, we are Super Resolution. I'm Aquino.
I'm Anderson. So what is super resolution? Super resolution is a process of turning a low resolution image to a high resolution image. So there are two types of resolution, the low pixel resolution. The pixel resolution is defined by the amount of pixels in the picture, and the spatial resolution is defined by how distinct the pixels are.
So super resolution is very important for some of the zooming in for satellite images or like medical images to see the cells and molecules.
Okay. And the data set we used is an online data set called DIF2K. It has 800 images of various types, including landscape, people, food, wild animals. And for each of the high-resolution images, there are 6 low-resolution images, each downscaled by a different method. And how we process this data is we crop each of them into two halves, and then we crop all of them into the exact same size to fit into the network. And the network we used is a GAN. So first we have the data set. It divides into the low resolution image and the high resolution image. And then the low resolution image is passed into the generator, and it produces the output image. And we feed both of them into the discriminator. The discriminator gives like the decision, and like the loss feeds back to the generator. And we have tried both the swish activation function and the leaky ReLU function. And both of them perform pretty well, but we chose to go with the swish activation function, and it's differentiable at 0. And the optimizer we used is Atom Optimizer.
So both our generator and discriminator is fully convolutional, both having the first CNN to expand the channels from 3 to like around 20 so that the more filters can be landed. And then for the generator, we used 18 residual blocks, which is the repetition of 2 convolution layers and 2 batch normalization layers to learn different kinds of features. And then at the end, we used a convolutional layer and a batch normalization layer to actually create the image of size equal to the high resolution image, and so that we can create a high resolution image out of the low resolution image. For the discriminator, after expanding the channels, we used around 8 repetitive blocks of CNN and batch normalization layers, including the swish activation functions mentioned earlier, so that the discriminator could ultimately decide whether the inputted image is real or like generated by the generator, which will be passed into the sigmoid function to make it a probability.
And here are some of the qualitative results. So the bottom 2 would be the high resolution image. The one on the left is at the very early stage of training the GAN. So we can see it has got some of the shape. However, the color is completely wrong. And the right one, this one, the one on the left side would be the generator's generated image. So it has started to recognize the colors and the patterns. And the top one here is our baseline. So our baseline basically expands the pixel size by 4 times in each dimension, and then it uses the average to calculate. And one way we use to measure how good the image is by mean opinion score. So we ask a couple of the friends, and they rate the pictures out of 5. And the first one, we got a rating for 0.5. And the second one, for both the baseline and the GAN, they rated around 3.5.
Yeah, and then mean opinion score is out of 5 usually.
Yeah.
And
now we also run it through the test image. So the left one is a generated test image, the middle one is a low resolution, and the right one is a high resolution. And so we can see the pattern is definitely being recognized and created. However, the color appears to be slightly lighter than the actual image. And here is a graph for the generator's loss. So we can see it trained very fast at the beginning. So the generator start to recognize the patterns and the colors very, very fast. However, then there's a very mild decrease in the generator's loss function.
another way we measured the model's performance was using a PSNR value. PSNR is peak signal to noise ratio. And that basically takes into account the mean square error of each pixels and also like the high resolution, low resolution comparison. So the higher the PSNR values, the better And then so for, as you can see from the graph, the PSNR value is indeed increasing as we train it more. So our training is working from this graph. And for our generated image, it scored around 21.3. Comparing this, usually the very high resolution image score around 50 to 80, a very compressed image score around 30 to 50. And so our generated image is not that great, but comparing to our baseline model, which scored around 9, it's quite better. And then at the end, so we learned that indeed GANs are hard to train, especially because at first the generator does not know what to generate. So next time we could either train the generator separately, as we discussed earlier, and also we could also increase the number of residual blocks in the generator so that we could create a deeper network to train. And as you could have seen before, the generator or the GAN it seemed like it was not learning the colors as we wished. So, but this can be improved by training it more.
Interesting. It's a hard thing to do, and you're right, GANs are difficult. A question, if you could go back to your model slide where you were showing the residual block and then the upsampling.
Yeah.
Do you have an intuitive sense of what the residual block is doing? Maybe that's a place to start.
Yeah, so each convolutional layers has like a same input channel number and output channel number. So basically, during that time, the model is learning all the features that it already learned, and also learning it more, I guess. And
It's learning the features.
yeah.
Because the way you created the GAN, you didn't start with the traditional random vector or an encoded vector. You started with the low resolution image, and then you're sort of encoding that into something smaller. Is that what's going on with the first layer, and then you're growing that?
So the first CNN layer before the residual network basically expands the channels from the low resolution image, so that ultimately you can create a high resolution image.
So the thing that's going into the residual block is the final resolution, and then somehow the final resolution, or
No, it was an expanded version
It's
of
even
the
lower.
lower resolution.
but not the final resolution.
No.
Some somewhere in between.
Yeah.
And then the upsampling takes you the rest of the way. Okay. It's good to see that, by the way, the qualitative and quantitative results. Could you go to one? No, we'll skip that. In fact, we're short of time, so we're going to have to do a really fast question.
Okay, I'll be quick. Residual block, did you add the skip connection? Is it just not illustrated here?
Yeah.
Okay.
Yeah.
Also, what kind of upsampling did you use?
Oh, it was just like a normal CNN batch normalization to expand the size.
So the upsampling block?
Yeah.
Like transpose convolution or like
No,
pixel
it was a
shuffle?
normal convolution.
Okay. And why did you use a fake test image? It seems like almost too easy of a task for that fake test image to
Oh,
be.
fake image is what the generator created
No,
using the lower resolution.
The one with the stripes that you created.
Oh, we just took
Yeah,
like
that.
that's just how we just asked it to like take a random test image and produce it.
That was a random test image.
Yeah.
Oh, okay. All right. Okay. I thought you guys made that. Okay, I got it.
Great, thank you.